Pluto is a far-off and puzzling planet that was once essential to our nearby planetary system's family. However, recent declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They propose that this freezing world is on a possible collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we seeing a looming crash, or is there something else about this approaching cosmic encounter? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet partly due to its exceptional orbit, remains a subject of interest and study in the cosmic community. Recent estimates by leading experts suggest that Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potential catastrophic impact between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it has yet to complete one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination. It is tilted at 17 degrees to the ecliptic plane. This means Pluto follows a much steeper path compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging our expectations about their positions in the solar system. This naturally raises the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unusual path. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's trajectory stood out with its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit does, in fact, cross Neptune's. The complexity of Pluto's orbit is a testament to the intricate mechanics of celestial motion. The three-body problem in space explores how three objects, such as Pluto, Neptune, and the Sun, move and influence one another through gravity. It's like predicting where they will go based on their initial positions and mutual gravitational pull. For Pluto's situation, this problem shows how its orbit, Neptune's path, and the Sun's gravity all work together in a highly complex way. The terms alpha libration, longitude libration, and the VZK effect are crucial to understanding this phenomenon. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. Regarding Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Longitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional layer of protection from potential collisions. Another significant factor in this scenario is the VZK effect, named after three researchers, Viktor Zaysov, Leo Kolshevnikov, and Kai Zhan. They studied how celestial objects influence one another through gravity. The VZK effect explains how three bodies, such as Pluto, Neptune, and the Sun, interact gravitationally in a way that maintains stability. Despite Pluto's orbit appearing chaotic, this effect helps keep it moving smoothly over time. The VZK effect shows that even though space may seem wild and unpredictable, certain patterns and rules maintain order. These factors work together to stabilize Pluto's orbit, ensuring it does not collide with Neptune or deviate dangerously. This three-body problem helps us understand how these orbits evolve based on the gravitational interplay between celestial bodies. Studying it helps us learn more about Pluto, our solar system, and even distant stars and galaxies. In the late 1980s, mathematical simulations revealed that despite these stabilizing factors, Pluto's orbit is still relatively chaotic. Small variations in initial conditions can lead to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over exceptionally long timescales, effectively keeping chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes, Neptune completes 3. This gravitational resonance helps keep Pluto's orbit stable. However, Neptune is not the only planet contributing to Pluto's stability. Jupiter's gravity also plays a major role in protecting Pluto's orbit, and Saturn contributes significantly as well. These simulations show that Jupiter's gravitational pull alone is strong enough to keep Pluto on a stable trajectory for billions of years. It appears that Neptune, Jupiter, and Saturn work together to ensure Pluto continues to move safely through space without running into trouble. These gravitational forces are crucial to maintaining order in the universe. Without them, the solar system as we know it would be far more chaotic and unpredictable. Celestial bodies like Pluto could collide with others or be ejected from their stable orbits, causing a domino effect on other planets and moons. For Pluto, especially in discussions about a possible future collision with Neptune, understanding its orbit is vital. This provides a clearer picture of the dynamics of our solar system. Pluto's case demonstrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and research to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this phenomenon. The concept of orbital chaos, where a celestial body's trajectory is highly sensitive to initial conditions, is vividly illustrated in Pluto's case. This means that even minor changes in Pluto's position or velocity can significantly alter its long-term path. In the vastness of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has been extensively studied, leading to significant discoveries about its structure and behavior. One of the most fascinating aspects of Pluto is its surface, which is a complex mix of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided stunning data about this distant world. Pluto's surface features vast plains, towering mountains, and deep valleys. One of the most remarkable features is Sputnik Planitia, an enormous heart-shaped plain primarily composed of nitrogen ice. This region showcases a diverse array of geological formations, including massive ice sheets and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active, despite its great distance from the Sun and its frigid temperatures. Another intriguing aspect of Pluto is its atmosphere, which is primarily composed of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin yet exhibits fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interactions between Pluto and its environment. During its closest approach to the Sun, some atmospheric gases may freeze onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit around a common point in space, rather than Charon simply revolving around Pluto. This unique relationship adds to the intricate gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt serves as a reservoir of ancient material from the early solar system, providing scientists with insights into its formation. Pluto's orbital characteristics may offer clues about the evolutionary patterns of these distant objects. Interactions with larger planets may have played a crucial role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is its potential impact on our knowledge of the solar system's evolution. Gravitational interactions with neighboring giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including Pluto. By studying Pluto's orbit and its interactions with Neptune and other celestial bodies, scientists can gain valuable insights into how planetary systems evolve over time. The delicate gravitational balance that keeps Pluto from colliding with Neptune also provides a window into the broader mechanics governing planetary motion across the universe. One of the most intriguing aspects of Pluto's orbital dynamics is the long-term stability it maintains despite its chaotic nature. While small perturbations could, in theory, lead to significant changes over millions or billions of years, the gravitational resonance with Neptune acts as a safeguard, preventing a catastrophic collision. Could Pluto ever collide with Neptune? Despite its seemingly precarious orbit, current simulations and observations indicate that Pluto and Neptune will not collide in the foreseeable future. The 2:3 resonance between the two bodies ensures that Pluto's closest approaches always occur at safe distances. Additionally, the inclination of Pluto's orbit means that even when it crosses Neptune's path, it does so at an altitude that keeps the two bodies apart. However, over extremely long timescales, on the order of billions of years, subtle gravitational influences from other planets, particularly Jupiter and Saturn, could introduce variations in Pluto's orbit. These small changes, compounded over time, might eventually disrupt the stable resonance, leading to a more unpredictable trajectory. Even if such an event were to occur, a direct collision with Neptune remains unlikely. Instead, Pluto could be ejected from its current orbit, either moving into a more distant path around the Sun or potentially being thrown into interstellar space. The broader implications of Pluto's orbit. Understanding Pluto's motion is not just about predicting its future, but also about gaining deeper insights into the dynamics of our entire solar system. The study of celestial mechanics, orbital resonances, and gravitational interactions help scientists model the movements of exoplanets in other star systems. Moreover, the Kuiper Belt, where Pluto resides, is home to countless other icy bodies that may share similar orbital complexities. Investigating Pluto's behavior can provide valuable clues about the evolution of other dwarf planets and Kuiper Belt objects, offering a glimpse into the early history of the solar system. The future of Pluto research. With advancements in astronomical observations and computational modeling, researchers continue to refine their understanding of Pluto's orbit and its interactions with other celestial bodies. Future space missions, potentially involving orbiters or landers, could provide even more precise data on Pluto's surface, atmosphere, and internal structure. As new discoveries unfold, Pluto's unique status in the solar system remains a source of fascination. Whether classified as a planet or a dwarf planet, its complex orbital dynamics and geological mysteries ensure that it will continue to be a subject of scientific interest for generations to come.